So derivative of 10 times x to the 24th. I know you all know it. I know you know it's 240 times x to the 23rd, but I also know that you know it's really 10 times 24 times x to the 23rd. And then we multiply. The reason I point this out is because when you're faced with something like this, you can use the same sort of idea. And this is really just, come on in, 24x to the 23rd over 10. And the reason that's true is because we're really taking the derivative of 1/10 times x to the 24th. And then it's just a constant multiple. The 1/10 hangs out. You get 1/10 times 24x to the 23rd. And then that's equal to 24x to the 23rd over 10. So when you have a quotient like that, if the denominator is a constant, it's just like multiplying by a constant. Dividing by a constant is like multiplying by a constant. It just kind of sticks around, or as I say, it hangs out. So just like the 10 hangs out here, the 1 over 10 hangs out here. And then you could simplify it. I don't know, like do 24 over 10, sure, that reduces to something. We don't care. Product rule, x cubed times e to the x. The derivative is going to be 3x squared times e to the x plus x cubed times the derivative of e to the x, which is e to the x. Yeah.
Am I also able to multiply it by 10 to the -1?
That's also, yeah. So you could totally write this as the derivative of 10 to the -1 times x to the 24th. And then the same rules apply. It's still just constant hangs out, take the derivative. Sorry, 23rd there. And then you could leave it like that, although it looks kind of funky, or you could rewrite it as 24 over 10 times x to the 23rd. And you can put that x to the 23rd either in the numerator or out to the right of the fraction. Either way is correct. To me, the easiest way to handle a problem like that, or the least amount of work, is to be like, oh, I've got a function divided by a number. I'm just taking the derivative of that top part and leaving the number away. That's a totally different case if the denominator is some sort of function of x, right? Then we actually do need to probably use the quotient rule. Don't miss your mouse. Okay, come on. So, on the last one here, sine to the 4th of x cubed plus 5x squared. We want to rewrite this as the derivative of sine of x cubed plus 5x squared raised to the 4th power. And then we're going to use the chain rule. Whoops, sorry, you can't see that. We're going to use the chain rule at least a couple times, I think. Let's see here. I should do the thing. I always do this, then I undo it somehow. That's better. Thanks, Seymour. The derivative of some stuff to the 4th is 4 times our stuff to the 1 less power. Thanks. Multiplied by, of course, as always, the derivative of the stuff. And the derivative of sine of something. Oh, I didn't see. Sorry. Thanks. There's sine of something is cosine of the something. Then we have to multiply by the derivative of the something, which is 3x squared plus 10x. That's how we would do the derivative of that. And let's see. Seems like a good opportunity to have you guys practice a little. Why don't you all try this one? Find the derivative of tangent squared of x cubed plus 5. Try that on for size. And I would definitely encourage rewriting. You're going to walk around and look at what you're writing. Oh, maybe. Might just be misread that, right? It's an execute, yeah. And since it actually is effective.
Oh, okay.
Yeah. Looking good. Excuse me. So once again, we've got the derivative of a function of a function. In this case, we've got some stuff squared. The derivative is going to be 2 times your stuff. Welcome to the first power. Thanks. Times the derivative of stuff. Derivative tangent of something is secant squared of something. But then we have to multiply by the derivative of the something, which is going to be 3x squared. That's it. Let's see. So I should mention there are 2 ways of writing the chain rule as a rule. And they're both useful in various ways. Now, I don't think you really, that's not true. Most of the time, what you should just do is what we would do, right? Like, for example, if I want to find, thank you. If I want to find something like the derivative of e to the tangent of x squared plus 9x, I'm just going to do the thing we always do and say it's e to the stuff. We know the derivative of e to the x is e to the x. So the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Right? That's the very kind of basic thing I think you should always do when you're thinking about using the chain rule. And then we're putting it in. Normally we're not writing this. Right? Normally we're just being like, I know how to find the derivative of that. So normally I'd say it's e to the stuff, which is e to the tangent of x squared plus 9x plus e times the derivative of stuff. And the derivative of tangent is, well, I really shouldn't say that. I said the derivative tangent of something, right? It's not just, never just tangent, right? It's always tangent of a thing. So the derivative tangent of some other thing is secant squared of the other thing. And then we multiply by the derivative of the other thing, which is 2x. And whenever you're thinking about just taking the derivative of something, this is normally how I would approach it. Obviously, right? This is how I've done it like every time. Of course, I would do it this way. But sometimes people like to ask funkier questions. And so even though I wouldn't normally approach a chain rule problem this way, you should be aware of the different couple of ways of writing the chain rule as a formula. So let's say we've got something like this. Y equal to, I'm going to do sine to the 6th of x to the 4th minus 1. And I'm thinking of this as some stuff to the 6th power. And we already know what the derivative is going to be. The derivative is going to be 6 times our stuff to the 5th power times the derivative of the stuff, which I'm actually going to leave as a derivative for just a moment. And then finally, we're going to write it all out. 6 times the thing, the power, and the derivative of sine of the stuff is going to be cosine of the stuff times the derivative of the inside stuff, which is 4x cubed. Okay. Sorry. It's a good example, but it's actually, I apologize. I was trying to show you guys something else and I was looking at the wrong page. I'm like, this example seems really complicated for what I'm about to show them. It's because I was looking at the wrong problem. But still, good practice, right? Pretty good. Let's actually look at the thing I was talking about. Here's a much easier example of the chain rule. So let's say we have a function like this. Y equal to x cubed minus 2 to the 7th power. Only a one-step chain problem instead of a two-step chain problem. So the normal way, right, if I was just taking the derivative, I would say y prime is 7 times my stuff to the 6th power times the derivative of my stuff. However, there are things people like to do. One way of attacking this, again, I don't really recommend either of these in general. But sometimes people do this thing where they're like, I'm going to call the inner function a different function name. Sometimes they call it g, sometimes they call it u. Those are kind of the common choices for the inner function name. So people might take this y equals x cubed minus 2 to the 7th and rewrite it as y equal to u to the 7th, with the knowledge or the assumption or the choice that u is equal to x cubed minus 2. It's still the same thing, we're just writing it differently. Okay, because now we're going to use this formula, which is that instead of writing y prime, I'm going to write the derivative using the Leibniz notation. And I'm going to say the following. dy dx is, well, here's the nice thing about this formula. This formula actually is a nice formula. It looks nice. It looks like if you were actually thinking of these things as fractions, they would cancel out in the appropriate way. We're going to get dy du, the derivative of y with respect to u, times du dx, the derivative of u with respect to x, which I think we can all see. Well, wait up, let's actually see this. So dy du, well, if y is equal to u to the 7th, what's the derivative of y with respect to u? I'm just asking for the derivative. It's 7u to the 6th. And if u is equal to x cubed minus 2, then du dx is going to be exactly what you think it is. It's going to be 3x squared. The thing that people don't like about this is that you've got this kind of intermediate step. You say, okay, I've got dy du, which is 7u to the 6th, times du dx, which is 3x squared. And it never feels good to leave it that way because you've got your derivative in terms of more than one variable, whereas we knew the original function was in terms of x. So we have to take the additional step of rewriting u as what we know what we said was equal to, which is x cubed minus 2. This is going to equal 7 times x cubed minus 2 to the 6 times 3x squared, which is the same answer. You might be asking, James, why would you do it this different way if your way is so much better? Like, right, my way is so much better. But sometimes, especially when we talk about related rates, using this formula is really, really easy to see what's happening. Also, when we get to 17C, when we talk about functions of multiple variables and there's a chain rule for that, then knowing this formula specifically actually is very useful. So when we get to functions of like x and y, and then x and y are functions of something else, we're going to see this sort of deal actually quite a lot. So this will come back. The other way of writing the chain rule, do I have enough room? Yeah, probably have enough room here. Is this is where we use g instead. So we're going to say that for y equals x cubed minus 2 to the 7th power, we're going to call the inner function g of x. So we're going to say that g of x is x cubed minus 2. And we're going to call the outer function f of x. So f of x is x to the 7th. Although some people say it's f of u or f of g, depending on what they do. But this is pretty standard. So if we look at this, it's true that f of g of x is x cubed minus 2 to the 7th power. We're plugging in x cubed minus 2 into the function f, which is being raised to the 7th power. Why would you do this? Well, because then you can just throw the formula at it if you've taken the time to memorize the formula. The formula for the derivative of f of g of x is f prime of g of x times g prime of x. Or as I would say, you should say, the derivative of the outer function, leave the inside stuff alone, multiply by the derivative of the inside stuff. And it's the same thing every time. So then we could be like, okay, well, f of x is x to the 7th. you know that f prime of x is 7x to the 6th. So f prime of g of x is not 7 times x to the 6th, it's 7 times g of x to the 6th times g prime. And then replacing g with x cubed minus 2 and g prime with the derivative of g, which is 3x squared. Once again, no surprise, we get the same answer. So normally I would do it the way we've been doing it this whole time. But sometimes people like to ask sneaky questions where you can't do that. For example, also please stop me if you have questions. Okay. So let's say we had a question like this. Suppose we are given the following. H of x is equal to f of g of x. And we know that f prime of 2 is 5. And f prime of negative 3 is 7. F prime of 4 is 6. And g of negative 3 is 2. And g prime of negative 3 is 4. And they're asking us to find h prime of negative 3. I mean, here we can't, I mean, like, sure, it's good to know that the derivative of h is the derivative of the outer thing, leave the inside stuff alone, multiply by the derivative thing. That's just the formula. But we need to know the formula so that we can then find what they're asking us to find. So we want to find h prime of negative 3, which is going to be f prime of g of negative 3 times g prime of negative 3. Okay, g prime of negative 3, sorry, g of negative 3 is 2. So that's going to be f prime of 2. G prime of negative 3 is 4 times 4. And then f prime of 2 is 5. So we get 5 times 4, which is 20. That's our final answer. You might be wondering, why is there so much more information over here? To let you have a chance to make a mistake. And that's really what, like, they're giving you, you know, what, we didn't use this or this. Sorry, we didn't use this or this. They're giving you that in case you plug in the wrong thing here and get negative f prime of negative 3. And they're giving you this in case you say, oh, it's f prime of g prime of negative 3. You get f prime of 4. So, right, they're giving you, they're not going to make it super easy, right? They're like, here's the paths to make errors. So here's a place where you need to know the formula, right? You still, I mean, I feel like we totally could have done this problem without knowing the formula, as long as we know the derivative of the function is just the derivative of the outside, the inside alone, the inside. But it's also good to know this formula. So here is the chain rule formula. And then since we're here on this page of formula stuff, anyway, I'll just point out that if you have multiple functions that that you're, what is the word? That you are, yes, but specifically the way we're combining them is by composition. You have a composition of multiple functions, so not just, if you had to say the derivative of like f of g of h of x, which I would never write this way. I think this is incredibly terrible. I would write it as the derivative of f of g of h of x. I would still just apply the rules in the same sort of way. Right, this is, so I want to point out here, this function, we are not saying that f is equal to f of g of x. Sorry, we're not saying that h, I'm not saying this here. This is for this problem, new formula. So if we were taking the derivative of this, very, very generally, you guys all know how to do it. What's my outermost function? F, so it's going to be f prime of, what do I do with the insides? Leave it alone, keep it. But then what do I have to multiply by? You can be very general. You can just say the derivative of the stuff, right? I know that's what, oh, sorry, of course, knocking things around, right? The derivative of the inside, which is going to be, well, I'm going to take 2 steps to write this formula out. It's going to be the derivative of g of h of x. And then we're going to use the chain rule there. So we're going to get still this f prime of g of h of x times, now the derivative of g of h of x is just the regular chain rule. Differentiate the outer function, leave the insides alone, multiply by the derivative of the insides. And you can do that for as many pieces composed together as you want. It's just the same. Every time you multiply by the derivative of the inside stuff, excuse me, that inside stuff is more complicated than just a function of x. You keep doing it, and you keep doing it, and you keep doing it. Okay. Where'd you go? Other notes I had brought. Oh, there you are. Good. So I'm not exactly sure where everyone's at right now. Has everyone talked about the chain rule in their classes? Let me ask the question in a more easy way. Has anyone not talked about the chain rule in their classes? Okay, that's all right. Okay, I mean, here's the thing. Either way, you're definitely gonna talk about it. So even if you haven't talked about it yet, you're definitely gonna get there soon, if you haven't already. So then, has anyone started talking about implicit differentiation? Just today. Okay, good. And how about derivatives of, don't worry, implicit differentiation is just the chain rule. It's really just another way of seeing, your teacher might not have said this, but I promise you, implicit differentiation is just the chain rule. We'll talk about it. It's not as hard as they probably have made it seem. The other thing I want to ask though is, let's do this first, and then we'll talk about implicit today because it can feel a little daunting. It's not as bad as it seems. But before we get there, let me ask you guys this question. Has anyone talked about how to differentiate 3 to the x? If I give the answer is no, it's not that bad. So the way I learned how to do this is probably different, but I'm gonna show you both ways. But the way that we can do this in this class is actually by just using a trick. I mean, you can do this in any class, but the way I've seen it presented in this class most often is to say, well, we know how to rewrite 3 to the x. We can rewrite 3 to the x as e to the natural log of 3 to the x. You can always rewrite anything as e to the natural log of that thing, as long as that thing is positive. It's kind of a weird truth, but it's true. E to the natural log of 3 to the x is just 3 to the x. But then we're going to use a logarithm rule. It says that x gets to come down in front of the natural log right there. So I'm going to write this as e to the x times the natural log of 3. And before we take the derivative of that, I'm going to ask you guys a different question. What's the derivative of e to the 6x? Do it on your own. I'll give you a moment. I would encourage you to think of it as e to the stuff. You are mostly right. You're missing a little piece. Times 6, exactly. Right, the derivative of e to the stuff is exactly e to the stuff times the derivative of the stuff. And we would usually put the 6 out in front, but nobody really cares. Okay, so the reason I'm pointing that out is because the same thing's going to happen here. The derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. What's the derivative of x times natural log of 3? Yeah, it's natural log of 3. Natural log of 3 is a constant. It's like the number 6. And so the derivative of natural log of 3 times x is just natural log of 3. Just like the derivative of 6 times x is just 6. The reason I mention this is because I've seen a lot of people over the years say like, oh, the derivative of natural log of 3 is 1 over 3. Because they know the derivative of natural log of x is 1 over x, and they're trying to put a 3 in there. It's not the case, right? The derivative, this is just And you guys, good job. You didn't make that mistake. That's just a constant. Constants, even if they look funky like pi or e or whatever, they're still just numbers that don't change. And the derivatives follow the same rules for constants. I should also mention, right, it's not 0, right, because it's not a constant by itself. It's a constant times x. And its derivative is the constant times 1. Okay. So what's kind of, oh, I should say, although you could leave your answer this way, I don't want to leave my answer this way. Because what do I know that e to the x times natural log of 3, what is this equal to? Well, it's that, which was that, which was that. So I could definitely write this as, and should write this as, 3 to the x times the natural log of 3. That's the more standard way of writing this derivative. And this formula, and it is a formula, is true for any positive base. I could have used 3, but I could have also used 8, or 1,000, or 1,000,000,000, or pi. We can say that in general, for f of x equal to a to the x, the derivative is a to the x times the natural log of a. With one caveat, a should be positive. And then, if we know how to take the derivative of something, there's automatically a chain-rule version of it, where we just take your x and replace it with stuff. So in a similar way, if f of x is equal to a to the stuff, then the derivative is a to the stuff times the natural log of a times the derivative of the stuff. A lot of books will use a u instead. Well, no books are using the word stuff, right? Like nobody's writing this in their textbook, right? But a lot of books will use u instead. So you might see this in a book as, for example, if you have the derivative of a to the u, it's going to be a to the u times the natural log of a times u prime. That's how a book might write it instead of like this funky way I'm writing it here. Either way, the idea is still the same. You've got a rule for a derivative. You can always just substitute in a more complicated thing for x and apply the chain rule by multiplying by the derivative of the more complicated thing at the end. So let's look at a couple examples. For example, here's an easy one. What's the derivative of 8 to the x? I don't want to rewrite it, although we totally could. I really just want to use the known formula that it's going to be 8 to the x times the natural log of 8. To me, that's the most straightforward way of doing it. If I want to take the derivative of something like 2 to the x squared plus 5, I could write it the long way, but I don't want to. I want to say I know the derivative of a to the stuff is a to the stuff times the natural log of a times the derivative of the stuff. So it's going to be 2 to the stuff times the natural log of 2 times the 2x. Yeah. That's weird. I usually don't put the natural log, I usually put the natural log of 2 last, but either it doesn't matter what order we multiply things in, so it's perfectly fine to put it there. So why don't you all try this one? Find the derivative of 10 to the x squared. I already used x squared. Let's say x to the 21st power plus cosecant of x. Try that one on for size. So again, this one hopefully isn't too bad. I've got 10 to the stuff. Derivative is 10 to the stuff. That's kind of a nice thing. If you ever have an exponential function, its derivative, the exact same thing should always show up. And if you've got some base to a power and the base is a constant, the power is a variable, that same exact expression always is there. And then there's some other pieces. So it's 10 to the stuff. I'm going to have a natural log of what? 10. And then the derivative of all this stuff, which is 21 times x to the 20th. And the derivative of cosecant of x is negative cosecant of x, cotangent of x. Cool. All right. We'll come back to this because we're going to see this again when we start talking about implicit. We probably won't get back to it today. We'll come back to it eventually. And we still haven't talked about the derivative of the natural log of x, have we? No. Okay. That's because there's a good reason why. I just want to make sure that no one's like said that so far. Let's go ahead and use a new page here. So let's say we had something that looked terrible. Let's say we have y equal to x squared plus 7x plus 1 to the 10th power plus e to the x plus sine of x plus 4 to the 8th power plus x to the 13th power, which is totally completely a function of x. We could take the derivative of this the long way. I mean, fine, it's not that. So let me show you, we will do it the long way first. It's not that bad. I'm going to take the derivative. It would be, let's see, 10 times my stuff to the 9th power times the derivative of the stuff, which is 2x plus 7, plus 8 times my stuff to the 7th power times the derivative of that stuff, which is e to the x plus cosine of x. And then x to the 13th is just x to the 13th. Its derivative is 13. However, what we're going to see is that it might be more convenient in the future to make these things less complicated. It might be useful to let, say, u equal x squared, x squared plus 7x. So kind of like we were doing with the chain rule before, where I was saying like this is kind of silly. Well, sometimes it's useful. We're going to let u equal x squared plus 7x plus 1, and we're going to let w equal e to the x plus sine x plus 4. Then I'm going to rewrite this function. I'm going to write it as y equal to u to the 10th plus w to the 8th plus x to the 13th. And now we're going to differentiate. So I'm going to ask some questions, and I think you guys know what the answers are. I'm going to find the derivative here. So I'm going to say it the wrong way first. That's okay. You guys can still tell me the answer. What's the derivative of u to the 10th power? Someone volunteer. I know you know. It's the question. It's the answer I want. Yeah. Thank you. Now, I didn't say a thing that I should have said. Because u really isn't just u. U is some stuff. So really, I'm taking the derivative of some stuff to the 10th power. And when I take the derivative of stuff to the 10th, I get 10 times my stuff to the 9th. And what do I need to multiply by? Thank you. The derivative of the stuff. Du dx. How about when I take the derivative of w to the 8th? Question, yeah.
Why don't you just put u with a little line?
With like the u prime?
Yeah.
That's also an option. It's really just most of the time it's a matter of preference. I'm writing it this way because I like to.
So like if I write that on a
Totally fine. Exactly 100. In fact, for the next here, for this next one, 8 times w to the 7th times, yeah, we say prime, w prime. Yeah, you can totally write it that way. It is equivalent in meaning. But sometimes this is nice, especially when we're seeing, like, for example, if I had written, I could have written this derivative as, yeah, I didn't know. That's not good, James. I'll just leave it there. You can totally use either notation. It's really fine. People like this because it feels a little more highfalutin sometimes. Like, I honestly, like sometimes people are like, this looks a little fancier. I'm gonna write it this way. This looks less fancy, but this takes up less writing. So most of the time I do kind of default to this, especially in the process we're about to use. And then what's the root of x to the 13th? Do I need to multiply by a thing here? No, I mean, you could be multiplying by the derivative of your stuff. Right? If you really want to think about this, you've got some stuff to the 13th. I know the stuff is x, but bear with me. The derivative of stuff to the 13th is 13th times your stuff to the 12th times the derivative of your stuff, which is 1. You can always use the chain rule. It's just that sometimes the inside stuff is x and its derivative that you're multiplying by is 1. But now look, this is exactly what we have up here. This is 10 times your stuff to the 9th times the derivative of your stuff, plus 8 times your stuff to the 7th times the derivative of your stuff, plus 13x to the 12th. So the point here is that sometimes we call a function of x by another name. I called this function of x, x squared plus 7x plus 1, I called it u. And when I took the derivative of u to the 10th, I took the derivative of u to the 10th and got 10u to the 9th, and then I had to multiply by u prime, or du dx. And I took the derivative of w to the 8th, I got 8w to the 7th, and I had to multiply by w prime. So when you take the derivative of something that has a function of x as kind of the stuff, you have to multiply by its derivative, which is just the chain rule, but which is also the key to making implicit differentiation work the right way. So this is really an example of how implicit differentiation works. And the reason it's called implicit differentiation is because usually you're going to be given something more like this, being asked to take the derivative, where it's implied, hence the word implicit, that these things are functions of x. But it's not ever explicitly written out like this, or like this, or like this. Let's look at another example. Don't worry, we've got enough time. We can get to the next 2 examples, which I think will make things a little bit more clear. So let's say, we have this circle, x squared plus y squared equals to 25, which looks like this. And I would really like to find the derivative, or I should say, let's say we want to find the slope of the tangent line at the point 3, -4, which is somewhere over here-ish. And first, we're going to do it by finding the slope explicitly, meaning we're going to solve for y, because occasionally that's an option. It's not usually an option. So let's solve for y. Y squared equals 25 minus x squared. Y equals, if I take the square root of both sides, I need a plus or minus. And that's where we kind of have an issue, actually. You get plus or minus the square root of 25 minus x squared. But if I'm down here, I know I want the which part? I want the minus part, because this part of the circle is the negative square root of 25 minus x squared, and this part of the circle is the positive square root of 25 minus x squared. So here is the function I'm going to be dealing with for the rest of this problem. Negative 25 minus x squared to the 1/2. Let's take the derivative. The derivative is going to be negative 1/2 times my stuff to the negative 1/2 power times the derivative of negative x squared, which is negative 2x. And simplifying just a little bit, the negative 2 and the negative 1/2 cancel. You get x divided by the square root. And then if I plug in x equal to 3, my prime evaluated x equal to 3 is going to give us 3 over the square root of 25 minus 3 squared, which is 3 over the square root of 16, which seems reasonable, right? It looks like the right kind of deal. Way more work than I want you to do, but I just want to show you that there's another way of doing this. So the whole idea with the second way is to keep in mind, we are assuming, even though it's not true, we're assuming that y is a function of x. Really, you could be a little more loose with the language. You say we're assuming y depends on x, which is true, right? Definitely, if I know what x is, there's only like a couple of things y could be, right? If x is 3, for example, y could only be 4 or -4. So certainly y depends on x. But I'm going to write it this way. I'm literally going to write y as a function of x. So now I'm going to rewrite this equation. Oops, this equation you can't see. X squared plus y squared plus 25. I'm going to write it as x squared plus f of x squared equals 25. And I'm not going to solve for f of x. I'm just going to differentiate the whole thing right now. What's the derivative of x squared? What's the derivative of some stuff squared? Two times your stuff to the first times the derivative of your stuff. What's the derivative of 25? Everybody, 0. So look, now the derivative that we wanted is showing up. And we can solve for that. So that's how this implicit differentiation process usually works in the beginning. You take the derivative of both sides of the equation, and then the derivative you're actually looking for, y prime or f prime, is present. And be like, oh, I'm going to use algebra to solve for that. So subtract 2x from both sides. 2 times f of x times f prime of x equals -2x. Divide both sides by 2f of x. Cancel the 2's. So f prime of x equals -x over f of x. Or if you prefer, changing back to y, y prime equals -x over y. And then we could plug in the point that we were given. The point we were given was 3, -4. And if we plug in 3, -4, y prime evaluated at 3, -4 is going to be -3 over -4, which is exactly what it was the other way. So the big idea for these implicit differentiation problems, which we're going to do another one of in just a minute here, is that when you look at this, it's always implied that y is a function of x. So whenever I see an implicit differentiation problem, I'm always thinking that y is just some stuff. Literally, those are the words, like y is stuff. And we know what to do when you take the derivative of some stuff cubed. It's 3 times your stuff squared times the derivative of your stuff. Let's look at an example. Ah, come on, thumbs. So yeah, let's look at this example. Let's say I want to find dy dx, aka y prime, for the following equation. X cubed plus y to the 4th plus tangent of y equals e to the y plus sine of x. Now I'll warn you ahead of time. The algebra for most of these problems is often pretty ugly. The calculus, on the other hand, is not that bad. The first step, always the first step, differentiate both sides. And remember or remind yourself, y is stuff. You could, if you really wanted to, rewrite every y as f of x. That helps, just like we did for the previous one. I don't think you need to do that, but you might want to. So now we're going to differentiate both sides. Derivative of x cubed is what? Little 3x squared. What's the derivative of some stuff to the 4th? 4 times your stuff cubed times the derivative of your stuff. Okay, what's the derivative of tangent of some stuff? Let's see, tangent is secant squared. Derivative tangent of x is secant squared of x. Derivative tangent of stuff is secant squared of stuff times the derivative of the stuff. I should have thrown in a y. All right. What's your e to the y? E to the y. Did I forget something? I did. Derivative of the stuff. Whenever you differentiate something that has a y in it, you end up having to multiply by the derivative of the stuff, which is y prime. The sine of x is cosine of x. So that's the first step. And the second step is algebra, all the algebra. So we want to collect all the terms that have a y prime term and bring them to one side, and all the terms that don't to the other side. So I would rewrite this as 4y cubed times y prime plus secant squared of y times y prime minus e to the y times y prime equal to cosine of x minus 3x squared. I would factor out a y prime times 4y cubed plus secant squared of y minus e to the y equals the same thing. And then finally, I would divide by this here to get y prime equal to cosine of x minus 3x squared divided by 4y cubed plus secant squared of y minus e to the y. It's not pretty, but it's just algebra. I know just algebra is maybe a bit of an overstatement, but it's not. It's algebra. It is doable. You just have to be careful with it. It's 3 o'clock. Let me show you one more. Just give me like 1 minute, just because there's one more thing I want to say. It's really, really fast. I'll just do it in this little corner here. If I was taking the derivative of, say I wanted to solve find the derivative for sine of xy equal to x squared. The derivative of sine of xy is going to be, well, I've got sine of some stuff, right? Because it's more complicated than just x. What's the derivative of sine? Cosine. So the sine of some stuff is cosine of the stuff times the derivative of the stuff. So the derivative of the stuff, I have to use the product rule, because x times y. So what's the derivative of x? Times, leave y alone, plus x times, what's the derivative of y? Well, here's the answer. It's the derivative of y. Right, y prime is literally the notation for the derivative of y. So the thing I want to point out here is sometimes when people are different, like if they say what's the derivative of y, you might be like, oh, well, it's 1 times y prime. But you don't have to say that. The derivative of y is literally the derivative of y, which is y prime. So when you're saying the derivative of y, don't get caught up. It's just like, oh, the derivative of y is y prime. If that's the only thing you've got, then that's the only thing you need to write down. And then there's more work to do, but I don't want to take more of your time. So we'll place this one on Wednesday. But the big takeaway for implicit differentiation is y is stuff. And when you differentiate something with a y in it, you have to multiply by the derivative of y at the end because it's really a function of x.